So we just apply the same, relation for electromagnetic fields. So we know that the electromagnetic field momentum density rho em is just rho em is just 1 over c squared times what? The pointing vector, right? We are talking about density. So if you want to find then the angular momentum density, if we know, let's say if P em is linear, the linear em momentum, then you can express the angular momentum just by applying that. LEM equals to R crossed with LEM. P. So you can write the momentum, the angular momentum density, so that's going to be log small LEM as R cross with rho em. So let's see an example that shows that illustrates real existence of angular momentum in electromagnetic fields. So this example, it really convinces you that actually there is angular momentum that is carried by the electromagnetic fields. So it says, imagine a very long solenoid with radius r, n turns per unit length, and it carries a current I. Coaxial with the solenoid are two long cylindrical shells of length L, one inside the solenoid at radius A that carries a charge plus Q, and this charge is uniformly distributed over the cylinder. And the other is outside the solenoid that has a radius B, and it carries charge minus Q. So this is basically what the problem is. So what you see here inside is a cylinder, and that has a radius A. It's inside the solenoid. And this, the bigger one, is also a cylinder, which is outside the solenoid. And what happens is next is when the current in the solenoid is gradually reduced, the cylinders begin to rotate. So find the torque responsible for the rotation and explain where does it come from. So what you just did is, there was a constant current that's flowing in the solenoid. You just start to decrease the current. When you do that, you see that these cylinders start to rotate. So what's responsible for the rotation? Whenever there is a rotation, you expect there is some transfer of angular momentum, whether it's mechanical or electromagnetic. So we don't have any mechanical, by mechanical we mean either you have to apply some external force by hand or something like that. There is no that kind of thing. All you did was just you reduce the current. So what is the source of this rotational one? So obviously it should come from the electromagnetic field's angular momentum. So we need to show that. So if we just look at the two-dimensional view from the top here, so if this is X, Y, so you have a solenoid. That has radius r. So this is radius r. So according to the diagram there, the current is rotating in a counterclockwise direction. So how can I show it here? It's gonna be that direction, right? So you have current flowing on this solenoid. So that's the direction of the current flow. I. So that would give you a magnetic field due to this current directed which way? Towards you. So you have, I can show that magnetic field with that. That's B. And inside this solenoid, you have another cylinder of radius A. So this one has radius A, and outside also you have another cylinder that has radius B. So that is B. So it says, the inner one carries a total charge that's uniformly distributed over the surface of class Q. So plus, 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 plus. So that is Q. And the outer one has a negative charge that's also uniformly distributed and minus Q. So just without applying the Poynting vector to find the linear momentum and then these to find the angular momentum, let's just think about torque in general, whether it is a mechanical force or electrical force. It's a result of some application of force, right? So let's find out what kind of force is responsible for the rotation and calculate the torque due to this force and find the net torque that's responsible for the rotation. And then we will apply what we discussed here about angular momentum that's carried by the electromagnetic field. Okay, so to find the force, first let's see what's happening here. When you cut down the current, basically you cut down the magnetic field, right? So when you cut down the magnetic field, you cut down the flux. When you cut down the flux, you induce the voltage. And the induced voltage